All right, so problem set number 8 is due. We'll have my office hours as usual tomorrow, so great opportunity to get that done. I won't be here on Friday. Alejandro surprise, and we'll have extra office hours then in the morning for you guys to discuss. Okay. But probably what's on your mind is the upcoming exam. So as I mentioned, I want to use lecture on Thursday as a kind of review session for the exam. We'll see where we are in lecture. We may have a little bit to finish up, and also have it as an opportunity to review. So I'd like you guys to think about coming with your questions so that I can kind of help where there are places that we would really like further discussion and explanation. So it's a lot of material. But so I made the decision that the focus of the exam is going to be on E and waves. Okay, so that's going to be the main focus of the exam. I won't have Biot-Savart law and microstress tensor.
We don't get to do a hands calculation of Biot-Savart law. What's even the point of it?
We can have extra credit. Who's gonna haze that guy after class? So that will, give you a little more focus on what to really study. Okay. All right. So let's continue on. So we're talking about thinking about wave propagation in matter. And in particular, if we have a dielectric where we only have bound charges, then we have a dispersion relation which will generally be of this form, okay? The relationship between omega and k is called the dispersion relation for reasons we'll see today. And in free space and the vacuum, this of course is 1, but in material, there is the material response is encoded in the dielectric constant, which is generally a tensor. We're not thinking about that at the moment, but thinking about it as scalar. And, but importantly, it's generally, in the way we write things, a complex number, okay? It has a real and imaginary part, which we'll re-emphasize today. And that means that the index of refraction is a complex number, which has a real part and imaginary part.
The dielectric constant, and you said there is a magnetic version of that, right?
Well, generally, it would be mu times epsilon. I'm taking this to be 1. So the general expression will look like this. So in general, as we saw many times, if we write out the macroscopic Maxwell equations, question: how do we get? Where the heck does the dispersion relation come from? How do you find the dispersion relation? You start with the wave equation, and then you plug in the plane wave ansatz, and when you write down the wave equation, it will have mu times epsilon in it, okay? And so this is the more general case. As I mentioned, in almost all situations, the magnetic, unless it's a very special material, the magnetic constant is close to 1, or close to mu. Unless you have a ferromagnetic material or a metamaterial which has been engineered. So most often, the magnetic response is negligible. But thank you, this is the more general expression. Okay, so what we saw thus is that there's a complex index of refraction, which is given by the square root of this complex number. And what that means is that when you look at, say, the electric field for, say, a linearly polarized electromagnetic wave, say, propagating in the z direction, which is given by this expression, then what you're going to find is that the amplitude is damped, right? So the intensity of the wave is attenuated, and the rate of attenuation is given here, and this is sometimes known as Beer's law, right? So the intensity as a function of z will decay exponentially with a decay constant, which is what?
Inverse of the stuff around z.
Yeah, times 2, right? This is the square of the field, that's the intensity. So the A is 2, right, at that frequency, and 1 over A, as you said, Donald, is sort of the decay length, okay? So the intensity decays, and, what kind of handwriting is that? And the wave number is modified by the real part of the index of refraction, which is to say that the phase velocity is related to the speed of light by the real part of the index of refraction. So omega over k real is the phase velocity, okay? Now, what we were talking about yesterday in my mind, our last lecture, was a model, the Lorentz model of a dielectric. Okay? And the Lorentz model of the dielectric is to say that we think about bound charges as a simple harmonic oscillator. This is linear response. It's linear because the restoring force is linearly proportional to the displacement from equilibrium, okay? And so we think about an electron bound on a spring to the nuclei, and there will be, when an electromagnetic wave propagates towards this particular, say, molecule or atom or solid, that you're going to get an induced dipole moment. Okay, so if this is the equilibrium position, we can think about R as the displacement of the electron from its equilibrium position. In quantum mechanics would say the atom stays in the ground state and then it's being excited. There will be induced dipoles, whether I describe it quantum mechanically or classically, and the induced dipole moment of this particular atom or molecule is equal to its charge times its displacement, right, from the origin, which we take to the equilibrium, and we'll take that to the origin, okay? And so if we have the induced dipole moment, we can get the induced polarization density, which is the density of induced dipoles. And we have the induced, and moreover, if this is oscillating at some frequency omega, then this will be oscillating at some frequency omega, at least in steady state, because we have a forced harmonic oscillator. And what we're going to find for linear response is that this thing is proportional to the electric field at the position of the atom. Okay? And this proportionality constant, so this is the linear response part. The fact that the induced dipole moment is proportional to the strength of the electric field is what we mean by linear response as opposed to nonlinear optics. And this proportionality constant is known as the polarized ability. Okay, it could be the molecular or the atomic polarizability depending on the thing that's being polarized. We could have a, we can think about a gaseous cesium atoms. I think about those guys all the time. Or we can think, well, I do, because that's what we have in the lab. Well, not my lab, but my imaginary lab. Or it could be in air. We can think about, oxygen molecules or nitrogen molecules, or we can think about a solid. Yeah.
So talking about the linear response.
Yeah.
I think in one of the lectures before, we saw that the polarization is proportional to electric field.
Not always. It is if we have a linear response.
If you have a linear response.
If we have a linear response, that's true. Yep.
Okay. And also here we say that for linear response, like the dipole moment is proportional to electric field.
Yep.
Through like the polarizability.
Yep.
So is there a relationship between the polarizability and the polarization?
So, okay, there's lots of different terms here. P here is the dipole moment of a particular. Now, if I have a whole collection, if I have a density, let's say N sub E is the density of electrons or molecules. These are the electrons that can be excited. Then the polarization density is equal to this. Okay, so capital P is what we call the polarization. I like to call it the dipole density. They're one and the same. This is the term that God knows who called this the polarization, but what it is the density of dipoles, okay? So that means, this is a very important point, we were gonna get to it, and I'm glad we'll get to it now, that I can write this, okay? So in this model, this is true if I can ignore local field corrections. Let me explain what I mean by this. This is true for a dilute gas. It's not true in a solid. It's not true in a dense gas, because what we're saying here is that the force of the electric field on this atom is just local, but there might be a nearby molecule which is polarized, and its electric field will affect its neighbor. So we're ignoring all the interactions between all the particles. And this is true if they're far enough apart from one another. And the dominant electric force is by the local field, but not what any of the other. Okay, so in this simple model, this is the case. So with that said, what we see here is that this is what we call the complex susceptibility.
N sub E?
Yes, I can always speak, yes. So the susceptibility is the density times the polarizability, okay? And the polarization has a complex amplitude given here. And as we wrote down, under the assumption of linear response, the polarization is proportional to the electric field. And that follows when we have a set of dipoles and the induced dipole moment is proportional to the electric field, okay? So our goal, thus, is to use the Lorentz oscillator model to write down what the susceptibility is based on mechanics, okay, of a forced harmonic oscillator. Very good. So what we wrote down last time, we said, well, the equation of motion is for a forced, damped, simple harmonic oscillator. So this harmonic oscillator has a natural resonance frequency and some phenomenological damping rate, okay? So omega naught is the resonance frequency. That depends on the atomic structure. And the equation of motion is what? What is the equation of motion for the position, the displacement from equilibrium? What's the differential equation? No, that's the equation for the propagation of the field. What I'm asking is, what is the equation of motion of the position of this electron that is being forced by the electric field? And it's a damped harmonic oscillator, which is, what is the equation of motion for a damped harmonic oscillator?
Double dot gamma r dot omega naught squared r.
Right. Equals the force per unit mass, all right? The force, the external force, and that is E. Only the electric force matters, and this is the electric force at the position of the atom. Okay, thank you, Donald. Everyone should be able to just write that down, okay? Okay, so that's the damped simple harmonic oscillator. And let's just, for the moment, take this at the origin. It wouldn't make a difference. That would just represent a different phase of the oscillator. If the electric field is a plane wave, there's a different phase at different positions where the atom is. Let's just take that phase to be 0 for simplicity right now. And so, you know, with the electric field at the atom as a function of time, oscillating like this, then in steady state, R is equal to something that is oscillating at the frequency of the drive. Not the resonance frequency. Yes?
Was there supposed to be a note above the R atom with the arrow? So second.
I'm taking this to the origin.
Okay.
Yeah, if I want, at the moment, yeah. Okay, so with that and that ansatz, we were able to solve for R tilde by just replacing every time derivative by multiplication by minus I omega, and this became minus E over M E tilde divided by omega 0 squared minus omega squared minus I omega gamma. Okay? Which means that the complex amplitude of the induced dipole is equal to E squared over M divided by omega squared minus omega squared minus I gamma times the electric field, okay? And this, my friends, and we're becoming friends, is the complex polarizability. Okay? So in the Lorentz oscillator model for a given resonance frequency, this is the polarizability. And we can then get the susceptibility by just multiplying it without local field corrections by the density. Okay? Yeah?
Does this approximation only hold if it's like hydrogen, we'll say?
No, this works for any molecules or gases where we have a sufficiently dilute system, as long as we'll come back to the question of multiple resonances. For the moment, let's just think we're thinking about a single resonance.
What do you mean by dilute?
What I mean is that the distance, the density is sufficiently low, the distance between the atoms is sufficiently high that the dipole moment that's induced on one does not have an electric field that affects its neighbor. Okay, so the only electric force I had was the force due to the field, not to its neighboring molecules or neighboring other parts of materials. Those are called local field corrections. Okay, we could do that, but this is a simple model, and it's a good model for a dilute gas. All right, so we also were looking at the case where on near resonance, near resonance means that omega, so let's call the detuning the difference between my frequency and the resonance frequency. And when this is much, much less than omega naught, then we could say that omega naught minus omega squared is approximately minus 2 times the detuning times omega naught to first order in delta. And omega gamma will also have gamma to be much, much less than omega naught. This is assuming the damping this is a high frequency compared to the damping. This is approximately omega naught times gamma. In which case, in this near resonance approximation, this is equal to E squared over 2m omega naught times minus delta minus I gamma over 2, approximately. Okay? And this then is this constant out front times minus delta over delta squared plus gamma squared over 4 plus I gamma over 2 delta squared plus gamma squared over 4. Okay. So, the polarizability has a real part and an imaginary part. Let's sketch them as a function of detuning. Okay? Okay. You're on a desert island. You don't have any cell phone service, and there's no batteries left on your laptop. And you have to sketch these functions as a function of delta. How do you do it? You could. I'm going to show you what the question is. A sketch. I want to do something kind of qualitative. So when you may want to sketch a function, the first thing you look at is what is its asymptotic behavior? How does it fall off far away from the origin? And what is it near the origin? And then you can just connect the dots. That's what you do, okay? So firstly, how does this thing look like when the magnitude of delta goes to infinity?
Drops off as one of them.
This goes of 1 over delta, right? Or, so this guy is equal to, when delta is much, much bigger than gamma over 2, this thing in that limit goes like minus 1 over delta, okay? Whereas this thing goes to what? 1 over delta squared, right? So we can just kind of sketch that and say, okay, there's something that goes like 1 over delta squared over here, and then something that falls off not quite as rapidly, right? And it's minus that, so on the minus side, it looks like this, and on the other side, it looks like that. So this is the imaginary part, and this is the real part. At the origin, what is the real part? And delta is 0. 0. And this thing is, yeah, so it's up there, it's 2 over down. So what we have, and this thing looks like, where this is small, it's got a quadratic term, so it kind of looks like this. It's an even function, first of all. And then this other guy looks like that. Because it's got a linear slope, it looks like minus, when this is small compared to this looks like minus delta, and this thing looks like that, okay? So, kind of developing a little bit, okay? So, this is the imaginary part of the polarizability, and that function is called the Lorentzian, after you know whom. And this is the real part. Okay? And this thing is where this matches, has a full width half maximum of gamma, which is sometimes called the line width of the absorption. Because of course, the imaginary part of the polarizability is related to the imaginary part of the index of refraction. And then this is known as the dispersive part.
Is this the part where we talk about group velocity?
We'll get there.
Okay.
Yeah. Now, what we see here is that this thing increases with omega, except within the band of absorption, where it decreases. So when the real part of this guy, when its derivative with respect to omega is greater than 0, we call that normal dispersion. And when it's negative, we call it anomalous dispersion, which we'll maybe say a few words about soon. But then for a absorptive medium, anomalous dispersion occurs where there's a lot of absorption. Okay. All right. Let's re-emphasize. We'll make it down a bit long, I'm sure. I'm the only professor who complains about this. Okay, good. And I am probably the only person who complains about a lot of things, but that is my style. All right. How do we understand attenuation and absorption? Okay, so attenuation means decrease in intensity of field, and my energy removed from field implies work done on charges. Okay, so let's think about this again. How do we understand this real and imaginary part business? So let's look at the say, the induced polarization or an induced dipole moment. Let's just take this at the origin. So that's the induced dipole. Yeah.
What's the word from dispersion?
Anomalous.
Anomalous, okay.
It's an anomaly. Typically, the real part increases with omega. This index of refraction increases with omega. But when it decreases, that's an anomalous dispersion. All right, so let's just take this to be for linear polarization. Take it outside here. Okay. What is the real part of this? If this were real, that would be cosine, but it's complex. So I can write this as the real part of alpha plus I, the imaginary part of alpha. Okay? And I plug that in. And so, yes, there is a term which is alpha times cosine omega t. I mean, the real part of alpha, excuse me. But what about this? This is a real number. This is I times that. What's the real part of I times that? What is the real part of minus I times, oh, plus I, excuse me, times that? Minus I times plus I is plus 1. This is plus sign, right? Again, I mean, we've said this many times, but I know it hasn't registered, so that's why I'm reading this very slowly. The real part of the complex amplitude tells you how much is oscillating in phase, and the imaginary part tells you how much is oscillating in quadrature. That's why, that's all that the complex is. It's just a way of encoding that. It's nothing crazy, it's not some stupid physics trick, it's math, okay? That's all why we do this. Fine, okay, so given that, I can ask the question, so now we have similarly the polarization capital P is equal to times the real part cosine plus the imaginary part sine. Okay, so the real part of the susceptibility tells you how much is oscillating in phase with the field, and the imaginary part tells you how much is oscillating in quadrature. Okay? Yes?
Does in quadrature just mean 90 degrees out of phase?
Yeah.
Okay.
Yeah, that's what it means. Okay. So now the question I ask is, what is the rate at which work is done by the field on the charges? That's what we call ohmic heating, right? And so I can think about that as J dot E. is equal to the rate at which right? What is the current density associated with this oscillating dipole, or set of oscillating dipoles? There's current because the dipole is oscillating, so there's moving charges, right? So how is the current density related to the polarization density for bound charges? That's the bound current density. In this case, this J is the bound current density. And what is the bound current density? It's the time derivative of the polarization. Okay? That's what we showed some lectures ago. The bound current density is the oscillating dipoles. So in this case, we can I'm gonna write this down again. So this is, I'm doing this all in real and not in complex. We'll come back to see how it connects to the complex. So let's just plug this in. This is then equal to minus omega, the real part of chi, sine, plus omega, the imaginary part of chi, cosine, E0 dotted into the electric field at the position of the atom, which we said was that.
Why do you switch from the complex notation to sine and cosine?
Because I want to show you that you don't need to if you don't like it, and what the heck it means, because it might all seem mysterious. So I want to do it in reals and then show you how it's trivial to do it in complex. So that's the method of my madness now. Because let's see how this works, okay? So what I have thus is equal to minus omega times the real part of this sine omega times cosine omega plus or minus omega, the imaginary part of chi, cos squared, E0 squared. Everyone with me? So that's the instantaneous, and now I'm going to take the time average of this. Okay, so I want to know what is the time average work averaged over a cycle of oscillation. You with me? What is this? What's the time average of cosine squared? 1/2. What's the time average of this? 0. Okay? So what we have found is that the time average of this is equal to 1/2 omega, the imaginary part of chi, E0 squared. The rate at which is proportional to the imaginary part of chi. Why was it proportional to the imaginary part of chi? Because the imaginary part of chi tells you the part that's oscillating in quadrature, but the absorption depends on the current. and the current is the time derivative, which then gets you back to cosine. So that's when you squared it, right? So that you need to have, you know, the current and the field oscillating in phase with one another, but or 180 degrees out of phase with one another in order to get absorption, right? The pushing of one on the other. Now, we can also write this as 1/2 the imaginary part of using our favorite complex notation. Everyone see that? Because this was equal, the time average of this is 1/2 I'm not sorry, not the imaginary part. The real part of this, solve that. Now that makes sense. So, let me do this a little more slowly. So, the time average of this, given dp dt goes to minus I omega p tilde, is this. Using the rules that time average of two functions that are oscillating as a function of omega is I take 1/2 the real part of one times the other, right? And this is then equal to omega over 2 times the real part of minus I chi omega E0 star dot into E0. Using this relation, which is equal to 1/2 omega, the magnitude of E squared, times the real part of minus I chi. What is the real part of that? It's the imaginary part. Voila, we got the same answer. If you don't like complex numbers, you don't have to use them. You could do this. They're the same thing. But isn't this easier? Yeah.
Where did the I omega come from in front of the polarization?
Hundreds of.
Because I took the time derivative.
Oh, I see.
So it was the current that mattered, not the polarization.
So sometimes you have an equation written down like on the homework, where we'll have a complex number times a complex number. That, a complex, like, if I wanna do something like P dot E, I can't just do the complex B times complex E, I have to use that conjugated time averaging trick, right? Because if I just multiply the complex numbers, there will be.
They are complex. These two numbers multiplied together are complex. So complex number times a complex number is another complex number.
But the real part.
But the real part is the real part of it. Every complex number, no matter what it is, has a real part and an imaginary part.
But,
So this is a complex number, but the time average I obtain as the real part of it.
well, I mean, is the real part of A times the real part of B isn't equal to the real part of A times B.
The real part of Z1 times Z2 does not equal the real part of Z1 times the real part of Z2.
Yeah.
So that's not what we did.
Yeah.
So what we do is we multiply them together and then take the real part. This would be equal to x1 times x2 minus y1 times y2 minus I x1 y1 plus x2 y2. If I wrote each one of these, the real part of this is this. So I didn't take, wait, this is a algebraic formulation that is really about sines and cosines. What this is about is sines and cosines, and how we take into account the amplitude and the phase by encoding the amplitude and phase of any oscillator. If I have any oscillator, A cos omega t, that is minus phi, that is equal to the real part of A e to the I phi e to the minus I omega t. And this is the complex amplitude of this function. But you can see, there is an imaginary part. It's just that there are only two numbers that define this oscillator. Its amplitude and its phase. And I encode that in a complex number. Or, I can think about it as having a real and imaginary part. The real and imaginary part of this number is A cos phi plus I A sine phi. This is the real part of F. This is the imaginary part of F. So this is equivalently A cos phi cos omega t plus A sine phi sine omega t. This is the imaginary part of F, and this is the real part of F. So when I write this number times this number, I'm not taking the real part of this times the real part of this. I'm multiplying them together, and this was x1, x2 minus y1, y2. And the algebra takes care of itself.
Okay.
All right. Excellent. All right. Very good. So, importantly, what we saw here is that the imaginary part of the polarizability here and the imaginary part of the susceptibility led to absorption, or leads to attenuation because energy is being absorbed and not going back into the field. It's going somewhere else. Where it goes, it can go into heat, or it could go into, the light could be scattered into other directions if it's re-emitted and not going into other degrees of freedom. All right.
You said the imaginary part of chi corresponds to absorption because of all that we just worked out.
Yeah.
That we got at the very end. It's the imaginary part that shows up in the time average of dissipation.
Yep. And the reason the imaginary parts are because the polarization is in quadrature, but the current is in phase with a minus sign, because the current is the time derivative. Yeah.
So the imaginary analysis of this is less about what is imaginary, what isn't. It's more just ways of categorizing two physically different things, almost like it. Could we just as easily just have not use I, but just say?
Yeah. Well, I just didn't use I here at all. Yeah. So that's what I was trying to get at. It's really about oscillating fields, and is it oscillating in phase or 90 degrees out of phase? Every function which is oscillating, let me try to say it one more time. Oh good, I have another board. Any function which is periodic with period t, any function like this is equal to that's the most general function I can write down. I can write this also like that. Those two are the same thing. So there's a part that oscillates in phase at cosine, and there's a part that oscillates 90 degrees. So any function that is periodic has this form. It's the most general form I can write down. Yeah.
So if phi is non-zero, then we get a sine of.
Yep.
So that's basically what it
Right, it's phase shifted relative to some arbitrary, right? So when phi is 0, you're right, this would just be cosine. Right? Now, this is equal to, just mathematically, the real part of A e to the I phi That's just a mathematical identity. Everyone see that? So instead of writing this all out in sines and cosines, we encode this in a complex amplitude and take into account amplitude and phase shifts through complex algebra, which makes things easier. If you don't think it's easy, don't use it. You don't have to. You can do it all in terms of sines and cosines, be my guess. But believe me, once you get used to it, it's much easier. All right, very good. So let's see. Where was I supposed to be? I might have forgotten. Right. Oh, I guess, yeah, okay, so there was a couple of things that I forgot that I just talked about. So I kept sort of relating this to the index of refraction. How is the index of refraction defined again? Because that's what we said at the very beginning of the class.
Root U epsilon?
Yeah, and we're taking u to be 1, so for a dielectric, it's that. Okay, and how is the dielectric constant defined in terms of the susceptibility? 1 plus 4 pi. Okay. So I kind of lied a little bit in, well, let's say for the dilute gas, we said this was equal to 1 plus 4 pi the density of this, forget about this W, times the polarizability. So I want to know what the real part and imaginary part of the index of refraction are. Now, I kind of lied and said that's just equal to the real, or it's just proportional to the real or imaginary part of chi, because the real part of the square root of a complex number is a complicated beast.
Didn't we have epsilon as some sum of tensors in the original equation we got it from?
I think generally this is a tensor, but at this point I'm assuming the response is scalar. The direction of the induced dipole moment is the same as the direction as if I had some kind of crystalline structure or something that responded differently, I have to think about that. But for the moment, I'm taking it to be a scalar.
Okay.
And in our simple Lorentz oscillator model, I assume no matter what direction I put the electric field in, the stretching was the same.
Okay.
Yeah.
And scalar is separate from it being linear. You could have a.
Yeah, that's nothing, that's different.
Okay.
I can have linear response and have it be tensor. Yeah, they're different, different conditions. All right. But if this is small, so again, I have a sufficiently dilute gas so that the density is very small. Oh, quick question. In these lovely units, what is the units of the polarizability? If n is a density, so n has the units of 1 over volume. What is the units of alpha, volume. Okay, so in Gaussian units, this has the units of volume. Here's an interesting question. If I were to think about a hydrogen atom, what would you guess the polarizability of a hydrogen atom is for hydrogen in its ground state? If you just had to guess.
12.
No, no, it may be in what units? Well, the question, yeah,
Well, I was gonna guess. I said like the Bohr radius, volume.
exactly. So the polarizability of hydrogen is about alpha naught cubed. That's exactly right. Because that's the only scale in the problem. You have to think about the scales. The atom's got the size of the Bohr radius, so that's why these are the best units in the world. Okay. All right, so where was I? Oh yeah. If this is small, then I can say that this is approximately equal to, I can use the binomial theorem to expand this and write it as what?
1 + 1/2.
Thank you very much. Right? Which means that the real part in this approximation, the real part of the index of refraction is 1 + 2 pi times the density times the real part of the polarizability, which in near resonance, you know, was and the imaginary part of the index of refraction is equal to 2 pi n times the imaginary part, which is Lorentz. Okay, so if I were to kind of sketch the real and imaginary parts of the index of refraction, what I would see is something that looked like this. Now this is the real part in this part, and this is the imaginary part. So we had this kind of dispersive, what we call this dispersive line shape, and right around resonance, there would be that. This is at some resonance omega naught. But typically, an atom or a molecule, not always, it's not a harmonic oscillator. It has multiple resonances. And so what we'll see is something that looks like this for a gas, for a different set of possible resonances that might have different line widths associated with them. And so there's an omega naught for different resonances. So this might be so there's a set of them. So a more general expression for the susceptibility might look like this. I'm going to write it in the following. I'll write it in the following way. Omega p squared is 4 pi n e over the mass of the electron. This is the plasma frequency. Where F is known as the oscillator strength. Okay. Now, the oscillator strength was put in by Lorentz, I think, as far as I understand history, as a fudge factor. Because when they measured the spectra and absorption lines of say gases, they found they had to put in a fudge factor here. And that fudge factor is really coming from quantum mechanics. The fact that it's not really a harmonic oscillator, it's orbitals, and you have to think about the superposition principle and stuff. And you can calculate the oscillator strength in quantum mechanics and get this kind of expression for thinking about the susceptibility of, say, a gas of cesium atoms, or what have you, word it. All right. I love the Lorentz oscillator model. It's really so useful in thinking about understanding material response and from sort of very simple principles, just harmonic oscillator. Yes, Omar.
So these are basically absorption spectra, right?
That's right, and dispersion.
Okay.
So this is absorption, and this is dispersion, which we're about to talk about.
If I think of the gas, completely quantum mechanically,
Yep.
then what's the explanation?
Well, I would have the same kind of physics, except that the response, the displacement of the position of the electron would be described by a position operator and a wave function, and I'd have to think about expectation values. But I can study that, and we will. Everyone's going to see me next fall in quantum optics, and we'll do that. Won't that be fun? All right, gosh, there's work to do. Let's go. We're talking now. I want to go beyond monochromatic. So all of this we've thought about a single frequency, okay? Let's just, for simplicity, let's just imagine to start, let's say we had two lasers that were beating together, okay? So let's just think about, just for simplicity, two frequencies. So now my electric field, say, let's say they're both propagating in the z direction, would be the real part of e to the I k z So I have two frequencies. Where k, as a function of omega, is n omega over c. And let's, for the moment, take this to be real. Let's say non-absorbing. We're in a, if I'm in this band over here, there's very little absorption, okay? Remember, the absorption falls off faster than the dispersion away from resonance. Okay, so I'm going to have two different indices of refraction and two different phase velocities, right? The phase velocity is omega over k. All right. So how do we rewrite? This is a cosine, this is a cosine, okay? And so now I want to think about this sum. I can write this in the following way. Let delta k equal k1 minus k2 and k bar equal k1 plus k2 over 2, and omega bar, or delta omega, is omega 1 minus omega 2, and omega bar is omega 1 plus omega 2 over 2. Okay? And so when we do that, I can rewrite this thing, the electric field, in the following way. This is equal to the real part of e to the I k bar z minus omega bar t times e to the I k bar, I'm sorry, delta k z minus, I did this right, hold on, let me get my notes, 'cause I skipped that. Okay, yeah, that's what, I wanted this over too. That makes sense, now it's right. Okay, if you multiply that out, times so this sum, if I factor out this overall product, I get the deltas. This is equal to twice the cosine of delta kz minus delta omega t. And so when all is said and done, this is equal to twice E naught times the cosine of k bar z minus omega bar t cosine delta kz minus delta omega t. Okay. So if I looked at the total electric field associated with two waves that are oscillating two different frequencies, it has this form. And if I were to sketch it, this is what it looks like. What I have is an overall envelope that oscillates at the difference and then in addition I have a beat note. The beat's going on here.
Is this E field per time?
This is the electric field, say at t equals 0 as a function of time. Or equivalently, I can think about it at t equals 0 as a function of z. Okay, let's think about it that way. Doesn't really matter. So what I have is this beat that's modulated by the difference frequency, right? This is what's known as the beat note. It's because I have this difference in the frequencies here that's describing this overall beating, okay? Now, how is this wave, which is not monochromatic, it's bichromatic, it has two frequencies, how does this thing propagate as a function of time? Well, let's just look at cos So this wave at a later time is what it was at an earlier time, having moved at this velocity, okay? Whereas the beat note moves at this phase velocity. And so what would this picture look like at a later time? What it will look like at a later time, if I thought about this, is that, well, this point will propagate a distance which is equal to V bar, I'm sorry, delta V, or it'll go a distance delta V times t at a later time, whereas this will propagate at a different speed. It'll propagate at this speed, which maybe is faster or maybe is slower. So it'll look kind of like this. In other words, what we call here the envelope moves at a different speed than this thing, which is called the carrier. Okay? So there is this difference of speeds, and the difference of speeds is coming from where? It's coming from the fact that k is not the same function, is not the same value proportional to omega. So k1 is equal to n1 omega 1 over c, and k2 is n2 omega over c, but the index of refraction isn't the same, which means that this velocity will not be the same as that velocity if the index of refractions are different. If there was no dependence of the index of refraction on frequency, these two guys would be the same. And the envelope and the carrier would move together. But because the index of refraction is different at different frequencies, this ratio is not the same as that ratio. Yes, Dave?
Was the beat note the envelope?
I would call the beat, it's a good question, what do you call the beat note? I don't know, I actually don't know whether I call that the envelope or the carrier.
Okay.
I think the whole thing is called the beat note. But the beat note consists of this carrier, which is oscillating at the mean frequency, modulated by this envelope. But the point I want to emphasize here is that because of the difference in the indices of refraction, we get this effect where the carrier and the envelope don't travel at the same phase velocity. And that is the beginning of dispersion, which we will finish up. You have in your homework, and we'll finish up on Thursday. All right? All right, thank you. Have a good rest of your day. I'll see you. Yes?
On the thing that I'm missing.
Oh, yeah.
Here.
You're
What's causing the modulation here? Is it a difference in indices of refraction? Or-
No, it's 60 here. two waves.
Which way?
These two waves. I'm adding two waves